This is video 42 in the lecture on the design of reinforced concrete beams. This lecture deals with design of prestressed concrete in SLS, and we will use the method Manuel. First, we have to make some assumptions. There is a linear elastic behavior of the concrete, or the law of Hooke is valid. A plane cross-section before loading is also a plane cross-section after loading, Bernoulli. The pre-stressing force is not influenced by external loads. The pre-stressing losses are 20%, and no external normal force is applied. And in SLSK, we will use the characteristic values of the forces. Suppose we have a cross-section. On this cross-section, there is a bending moment acting from the external loads. The pre-stressing force P acts with an eccentricity of E, and this means that the section is loaded in its point of gravity by a normal force P, a bending moment M, and another bending moment P times E. If you look at the stress diagrams, then you see for the compression, just the compression caused by the pre-stress, the stress is P over A. A is the cross-section of the concrete. We have stresses induced by the bending moment PE, and stresses and stress diagram coming from the external bending moments M. It's pure elastic design. We make here assumptions or sign conventions, and when there is compression, we say that the stress is negative, and the stress is positive. It means that there is tension. P, of course, is always positive. This is an external force. These are stresses. E is positive, like it is shown here. When it's below the point of gravity, E is positive. When it's above, E is negative. And V and V double and all those other elements are always in their numbers, it's positive. The bending moment is calculated as positive when there is tension on top and compression below. So a sagging bending moment is a negative bending moment. Remember now those four stress diagrams, one for the pre-stress, one for the pre-stress bending moment, and one for the external bending moments. Then we can write for the top fiber of a cross-section, we can say, okay, there is one portion compression, a portion tension, and against a portion compression, which is just the sum of those three. On the bottom, we can say the same. Remember, we said we will have no external normal force. If this is the case, then we should add here N divided by AC, and the same here, N divided by AC. If the external force is eccentric, then you also have N times E. So here again, we have compression, compression, tension. Compression, 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 tension. Now we can use the radius of gyration, which is defined by this. E is equal to AC times air squared. And we substitute for E. Then we have this equation. And this equation means that if E is bigger than air squared divided by V accent, then the outside then we are outside the central cross-section core. It means that there is tension by pre-stress. And when E is smaller than R squared divided by V accent, then we are inside the central cross-section core and there is compression by pre-stress. just have now a look of a cross section. Then we look at the bending moment at minimum permanent loads, MP, the total bending moment, MT, the initial pre-stressing force, which is the largest, and the pre-stress losses. Then we have a limit value for the compression force in the concrete. This can be 0.6 or 0.5 FCK. And we have a limit value that we choose for the tension in the concrete. It can be 0. It can also be a compressive force, in fact, or it can be, for instance, FCTM. So this is the design values that you use. Here, this value is in fact fixed. Once the concrete quality is fixed, this you can choose. Most commonly, you use 0, so there is no tension in the concrete. Once you've got that, then we can see for the top fiber, there is maximum tension in the top fiber when the initial pre-stressing force is applied, the maximum pre-stressing force is applied, because when this is maximum, then the tension there is maximum, and the minimum bending moment is applied, the bending moment at minimum permanent loads. So in this combination, you have maximum tension on top. You have maximum compression on the top when you have the smallest pre-stress and the total bending moment. MP and MT are such that there is tension on the bottom and compression on top, because it's marked here positive. Then on the bottom fiber, you can do the same. When is the tension maximum? That's when the pre-stress is minimum and the total bending moment is there. And the compression is maximum on the bottom fiber when the pre-stress is maximum and the bending moment minimum. You see that you have different combinations to calculate different stresses on top and bottom fiber. We can now rewrite those equations, and doing so, we have 4 equations. There is a fifth one, which means that, of course, the eccentricity E of the pre-stressing reinforcement must, of course, be smaller than V. Even smaller than this amount smaller, that you should have enough concrete cover and so on. So that's why it states E0 is smaller than V and E must be smaller than E0. Most commonly figures are 150 to 200 millimeters. So E, the eccentricity, must be smaller than V minus, let's say, 150, 200 millimeters. So now you have 5 equations. 5 equations where you can make a graph. On the x-axis, it's the eccentricity E, and on the y-axis, it's 1 over P0. It's 1 over the pre-stressing force. Then you have the 5 equations, and every point inside this figure is a point that complies with sigma T max and sigma compression minimum and maximum. So with the chosen values of the stresses, you can now calculate the needed eccentricity and the needed pre-stressing force. You can see easily on this drawing that there is no one solution. There are different solutions. You can use big pre-stressing force and a small eccentricity, or you can use a small pre-stressing force and a big eccentricity. We prefer to work in this region. Now, just bear in mind there are conditions to have a solution, and when we make a recap of the drawing, then you will see that of course line 3, this line, must be above line 4, otherwise you will not have that area with solutions. It means that E over V, which is giving you a condition on your shape, on your dimensions of the section, must be bigger than this value. And line 2 must be above line 1. Line 2 must be above line 1 or on the left of line 1. Gives you also a condition of E over V accent. So you have a condition over E over V and E over V accent. The E is initial and the U is final, ultimate. And then of course line 5, this line must be on the right of point G, otherwise this area will disappear. And A and B have those values. Now you have 3 conditions, 3 equations where you can estimate or give the boundaries of the dimensions of the cross section. You can do this for each cross section, and each cross section will give you a solution of the minimum eccentricity and a maximum eccentricity for a certain chosen pre-stressing force. And then you know that the profile of the tendon must be inside this area. If you do so, then you comply with your sigma max and sigma minimum. If this area is not wide enough or does not suit you, then you need another pre-stressing force and you have to do the recalculate the whole system. This lecture dealt with the design of pre-stressed concrete in SLS and showed how to use or apply the Manuel method. See you next lecture.